Data transformation.
The process of changing data from its original format to a new format is called data transformation. This process is usually done so that data can be easily understood or achieved to meet some other research objective.
For example, when the data is measured using scales, quite often the statements are given in negative as well as positive formats.
In such cases, the researcher will reverse code the questions that a negatively worded so a summated scale can be calculated to interpret the results.
If a scale of 5 is used, a 5 will be transformed to a 1 and a 4 to a 2. A 3 does not have to be changed.
Data transformation is usually done to reduce bias when ages of respondents are being studied.
To reduce the bias response, respondents are asked the year they were born.
In such cases, the researcher would have to simply transform the birth year to obtain the age of the respondents.
Data transformation is required when the researcher wants to create a new variable by respecifying the data according to logical transformation. Data transformation is required when the researcher wants to create a new variable by respecifying the data according to logical transformation. Usually, the transformed variable involves combining the scores, raw data, for several attitudinal statements into a single summated score.
The researcher could also calculate an average summated score that involves dividing the total summated score by the number of variables.
For example, if 3 5-point statements are used, the summated score might be 4 plus 4 plus 5 equals 13.
Using the average summated score, the result becomes 4 plus 4 plus 5 equals 13 divided by 3 equals 4.3.
Self-check.
Why do we need to transform original data? What kind of steps can be taken to minimize or avoid biases during the data analysis stage of research?
Data analysis.
The objectives of data analysis can be viewed from 3 aspects.
To have a feel of the data, to test the goodness of the data, and to test the hypothesis developed for the research.
Getting a feel of the data can be achieved by checking the mean, the range, the standard deviation and the variance in the data.
These statistics will give the researcher a good idea of how the respondents have reacted to each item in the questionnaire and how effective the items and measures are.
Suppose the researcher notices that the item in that data set does not have a good spread, range, and shows little variability.
The researcher can deduce that the question may not be understood by the respondents due to improper wording, or the respondents may not fully understand the intent of the question.
If the respondents have given similar answers to all items, the researcher may want to check for biases. For instance, if the respondents have stuck at only certain points on the scale.
The objective of descriptive analysis is to portray an accurate profile of persons, events or situations.
The analysis could be an extension or a beginner for a piece of exploratory research.
Summarizes data presentation by data type. Data presentation by data type. Activity.
What are the factors that determine the choice of data analysis? Compare your answers with those of your classmate.
Descriptive statistics.
In the first part of the topic, we have discussed how responses could be coded and entered.
When nominal measurements are involved, each category is represented by its own numerical code.
With ordinal data, The item's rank, reflecting a position in the range from the lowest to the highest, is entered into the system.
The same is true with interval ratio scores. When this data is tabulated, it may be arrayed from the lowest to the highest scores on the scales.
Together with the frequency of occurrence, the observations form a distribution of values.
Many variables of interest have distributions that approximate a standard normal distribution.
It is a standard of comparison for describing distributions of sample data and is used with inferential statistics that assume normally distributed variables.
The characteristics of location, spread and shape describe distribution. Their definitions, applications and formulas fall under the heading of descriptive statistics.
Although the definitions will be familiar to most readers, the review takes the following perspective on distributional characteristics.
A distribution's shape is just as consequential as its location and spread.
Visual representations are superior to numerical ones for discovering a distribution's shape.
The choice of summarized statistics to describe a single variable is contingent on the appropriateness of those statistics for the shape of the distribution.
Measures of location.
The common measures of location, often called central tendency or center, included the mean, median and mode.
Mean?
Mean is the arithmetic average. It is the sum of the observed values in the distribution, divided by the number of observations.
It is the location measure most frequently used for interval ratio data, but can be misleading when the distribution contains extreme scores, large or small.
Mean of the population, or population mean, is denoted as M, and is defined as
Median.
Median is the midpoint of the distribution. Half of the observations in the distribution fall above and the other half fall below the median.
When the distribution has an even number of observations, the median is the average of the two middle scores.
The median is the most appropriate locator of center for ordinal data and has resistance to extreme scores, thereby making it a preferred measure for interval ratio data, particularly those with asymmetric distributions.
Mode.
Mode is the most frequently occurring value. When there is more than one score that has the highest yet equals frequency, the distribution is bimodal or multimodal.
When every score has an equal number of observations, there is no mode. The mode is the location measure for normal data and a point of reference along with the median and mean for examining spread and shape.
Measures of spread.
The common measures of spread, alternatively referred to as measure dispersion or variability, are the variance, standard deviation, range, interquartile range and quartile deviation.
They describe how scores cluster or scatter in a distribution.
Variance.
Variance is the average of the squared deviation scores from the distribution's mean. It is a measure of score dispersion about the mean.
If all the scores are identical, the variance is naught. The greater the dispersion of scores, the greater is the variance.
Both the variance and the standard deviation are used with interval ratio data.
The symbol for the sample variance is S2, and the population variance is the Greek letter sigma squared, S2.
Standard deviation.
Standard deviation is the positive square root of the variance.
It is perhaps the most frequently used measure of spread, because it improves interpretability by removing the variances square and expressing deviations in their original units.
Like the mean, the standard deviation is affected by extreme scores. The symbol for the sample standard deviation is S, and a population standard deviation is S.
Range.
Range is the difference between the largest and smallest score in the distribution. Unlike the standard deviation, it is computed from only the minimum and maximum scores.
Thus, it is a very rough measure of spread. With the range as a point of comparison, it is possible to get an idea of the homogeneity, small std, dev, or heterogeneity, large std, dev, of the distribution.
For homogeneous distribution, the ratio at the range to the standard deviation should be between 2 and 6. A number above 6 would indicate a high degree of heterogeneity.
The range provides useful but limited information for all data. It is mandatory for ordinal data.
Interquartile range.
Interquartile range, IQR, is the difference between the first and third quartiles of the distribution.
It is also called the midspread. Ordinal or ranked data use this measure in conjunction with the median.
It is also used with interval ratio data if there are asymmetrical distributions or for exploratory analysis.
Recall the following relationships.
The minimum value of the distribution is the percentile and the maximum is the L percentile.
The first quartile, Q1, is the 25th percentile.
It is also known as the lower hinge when used with box plots.
The median, or Q2, is the 50th percentile. The third quartile, Q3, is the 75th percentile. It is also known as the upper hinge. The IQR is the distance between the hinges.
Semi-interquartile range.
Semi-interquartile range is expressed as
the semi-interquartile range is always used with the median for ordinal data. It is helpful for interval ratio data of a skewed nature.
In a normal distribution, a quartile deviation, Q, on either side encompasses 50% of the observations.
Age, QS, cover approximately the range. Q's relationship with the standard deviation is constant, Q equals 0.6745 s, when scores are normally distributed.
Measure of shapes.
The measure of shape, skewness and kurtosis describe departures from the symmetry of a distribution and its relative flatness, peepness, respectively.
They are related to statistics known as moments, which use deviation scores, x, Kissy.
The variance, for example, is a second power moment.
The measures of shape use third and fourth power computations and are often difficult to interpret when extreme scores are in the distribution.
Skewness is a measure of a distribution's deviation from symmetry. In a symmetrical distribution, mean, median and mode are in the same location.
A distribution that has cases stretching toward one tail or the other is called skewed.
Kurtosis is a measure of a distribution's peepness, flatness. Distributions where scores cluster heavily or pile up in the center, along with more observations than normal in the extreme tails, are piezoelectric.
Flat distributions with scores more evenly distributed and tails fatter than a normal distribution are called plateictic.
Intermediate ohmsectic distributions are neither too peaked nor too flat. The symbol for Kurtz's is Q.
What is a hypothesis?
In statistics, a hypothesis is an unproven supposition or proposition that tentatively explains certain facts or phenomena.
A hypothesis can also be an assumption about the nature of a particular situation.
Statistical techniques enable us to determine whether the proposed hypotheses can be confirmed by empirical evidence.
Hypotheses are developed prior to data collection, generally as are part of the research plan. Hypotheses enable researchers to explain and test proposed facts or phenomena.
The following are general steps in hypothesis testing.
Make an initial assumption.
Write down the null and alternate hypotheses.
Determine the level of significance, a level.
Collect evidence and perform the statistical analysis. And,
based on the available evidence, decide whether or not the initial assumption is reasonable and write the conclusion.